When you believe what everyone else believes, you run the risk of falling into the trap created by the fact that everybody else is doing the same. H2O is a polar molecule. H2O is a solvent, sometimes referred to as the universal solvent. You will have been told both of these things if you take a class in chemistry. But now let me tell you something you will not have been told. H2O is a solvent of its own polarity. And that when you understand it as being a solvent of its own polarity, you now have the means of understanding why the so-called anomalies of H2O are really not anomalies. They're just the fact that we have misunderstood H2O. So what we're going to do in this video is we're going to actually discuss why H2O is considered polar. We're also going to point out the mistake that was made that brought people to the conclusion falsely that H2O is anomalous. Now, the observations that our current theory failed to explain are very real, but what's really going on is that our current understanding of why H2O is polar is wrong. It has a fundamental flaw in it, and that's what we're going to explicate right now here on Solving Tornadoes channel. So we have an H2O molecule here. It's polar. But it may not be clear from looking at this picture as to why the individual H2O molecule is polar. So one little trick we're going to do is just show the nuclei, and here you're going to see some relationships of nuclei to each other. Here we have a situation where this nuclei is more electronegative, and this one here is less electronegative, and the net result of this is a net positive emanating right up here. Likewise here. And when we look at the other side of the molecule, we're seeing a net negative. And again, negative. This nuclei is pulling the singular electron from these hydrogen atoms, that's pulling it down. So if we were to go ahead and represent that, we could take this, that's positive, that's negative, and that's another negative, and we can see why H2O is a polar molecule. Now let's take a look at a non-polar H2O molecule. This is the same H2O molecule as before, but now it's non-polar, and in order to avoid confusion, we can look at it more like this. Again, this is a non-polar molecule. It's surrounded by other H2O molecules. Now, why do we say this is nonpolar? Well, one reason is because it's no longer producing a polar force. It's no longer attracting any of these other molecules because its polarity has literally been turned off by the fact that H2O is a solvent of its own polarity. Now, it may not be apparent to everybody why this is no longer a polar molecule. And what's interesting is the current paradigm assumes that H2O is always a polar molecule. And we can go ahead and do the same thing we did before and just represent the nuclei and show the relationship of nuclei. And let me first introduce how the current paradigm assumes that H2O is a polar molecule. They don't take into consideration what happens when other molecules come up and make hydrogen bonds. So here is the situation under the current paradigm, where they assume that H2O is a polar molecule even when it's surrounded by other H2O molecules, but actually it isn't, and here's why. Note that there's now a balanced arrangement of electronegativity surrounding this hydrogen atom, and the same is true for this hydrogen atom. The same is true for this part of the molecule, and for this part of the molecule, there's no longer any net electrical gradients in relation to the nuclei. We now have a very balanced arrangement of nuclei and of electrical gradients. They're perfectly balanced, and when they're perfectly balanced, there's no longer any net positive or negative. So H2O, when it's surrounded by itself, is a non-polar molecule. Now you say, well, why does it matter? Well, it matters because in this instance, it's no longer producing a polar force. That's the significant thing. It's no longer producing a polar force, and our current paradigm assumes that since it has this arrangement, our current paradigm says, oh, it has this arrangement, therefore it's always producing a polar force. Well, it's not always producing a polar force. It's only producing that polar force to the degree that it's not already surrounded by other H2O molecules, because when it is, that polar force stops. Now, you say, well, what difference does it make? Well, we have a confused paradigm. People believe things based on this arrangement. They look at the electronegativity differences and they say H2O is a polar molecule, and they don't put any thought into it after that. And that's why we're so completely confused in the science of water, and it's why we have this notion that there's all these anomalies. Well, the anomalies are complexities that are a result of the fact that when H2O makes hydrogen bonds with itself, its polarity is turned off, and therefore its behavior is going to be different. The most obvious behavior that's different when it's surrounded by itself is that it has such low viscosity. Think about it. If H2O had a permanent polarity, there's no way in the world it would have the low viscosity it does have. But what's strange is people just don't think about that. Instead, they get hung up on this notion that H2O is a polar molecule. And then when the evidence suggests something different is going on, they say, oh, well, that's an anomaly. And if you look into the literature on H2O, you find out it has multiple anomalies. So in its natural form, H2O has very low viscosity because it's surrounded by itself. But situational factors that take away some of that ability to surround itself do cause polarity to get turned back on. And it's when it's turned back on that we see behavior showing up that make us wonder, well, what's going on here? And so we're so completely confused on the fundamental level that we can't make sense of common observations. We end up creating this fiction around this notion that H2O has these magic anomalies, when really it's just ourselves being confused about very simple things. Why did the current paradigm become so confused about hydrogen bonding in water? Well, as I explained so far, they miss the fact that H2O molecules are a solvent of their own polarity, and that therefore they neutralize each other's polarity when they make hydrogen bonds. Now, you might wonder why something so simple was missed by so many people in the current paradigm. And I don't think it's simply because of what I just said. There's another complicating factor that I think prevented them from making the realization of the truth of what I'm saying. And that has to do with Coulomb's law. Let's go ahead and bring up Coulomb's law. This is something I found on YouTube. Let's go ahead and read this here. It says, the closer two charges are, the stronger the force between them. Now, if we know that H2O molecules, when they surround each other, they eliminate each other's polarity. So that would appear, from what we're seeing here, to be a violation of Coulomb's law. But let's make sure we don't make a mistake in what we just read here. It does not say the closer two molecules are to each other, the stronger the force between them. And I think it's the confusion between that interpretation and the correct interpretation, which is the closer two charges are, the stronger the force between them. Because, well, let's go ahead and bring up the actual equation, and I think you'll see what I mean. So here's the actual equation of Coulomb's law. In this equation, you see Q1, Q2, those are the charges. And normally when people consider Coulomb's law, the Q1 and the Q2 do not change. And they certainly don't change having anything to do with distance, because considering that the distance in this one is the r squared. But that's actually what's happening with H2O. As they come together, the difference between the positive and the negative disappears. It continues to disappear all the way up until they completely come up next to each other, at which case it completely disappears altogether. But I think what happened is people have this misunderstanding of Coulomb's law. They think it says that two molecules, as they come together, that the force between them will always get greater. And as we see with H2O, exactly the opposite's the case. And actually, it's not really exactly the opposite, because Coulomb's law still applies to the degree they are separated from each other, and to the degree that there is a difference between the positive and the negative. It just so happens, though, that as they come together, that difference itself between the Q1 and the Q2 in this equation literally disappears. And I think that, together with looking at H2O as a singular molecule with its charges only affecting from within the molecule itself, that was the first mistake. But I think this is the second mistake. It's the misconsideration of Coulomb's law, creating this false notion that what we're seeing couldn't possibly be the case. Actually, hydrogen bonding doesn't really have any contradiction with Coulomb's law, because again, Coulomb's law assumes that there's a stable Q1 and a stable Q2, and as distance decreases, that difference between Q1 and Q2 on this equation disappears. So I think together, these were the 1-2 punch that still to this day has most of academia confused on what's going on with hydrogen bonding in water. Now, in order to continue to make my case that the current paradigm of hydrogen bonding in water is a fundamentally confused paradigm because of that mistake, because of their failure to recognize that H2O is actually a solvent of its own polarity, I'm going to go ahead and take a look at some YouTube videos where they do their best to explain our current understanding, and I'm going to point out where they have incorporated some confusion into the larger narrative. Now, I found this one video, and it's by a gentleman named Wayne Breslin, and I want to make the point that this video is very good at explaining what the current paradigm is. Now, it contains the mistake, it contains the misthinking, and it does a very good job of explaining this misthinking, of making it explicit. So it's not the fault of this author, Mr. Breslin, that he's presented here as something that's actually confusing. He's accurately reflecting the confusion of the current paradigm.
When we look at a water molecule, it is a polar molecule. That means that one side has a positive charge and the other has kind of a negative charge. We call it a dipole. In this case, oxygen's more electronegative than the hydrogens. So this is going to be the negative side, and this is going to be the positive side. But the water molecule kind of has sides to it.
Note that he described the difference in electronegativity. This is kind of where some of the confusion comes in. They're failing to recognize the exact differences and the arrangement of electrical gradients to nuclei that is causing this force field, that's causing this to be a polar molecule. But actually, up to this point, this is pretty much exactly what I stated. But let's see what happens, though, when he starts to incorporate other H2O molecules.
This hydrogen bond, it's breaking and reforming.
Now, note how there's this distance between these two H2O molecules. And they draw this line, and he says something about the bonds breaking and reforming. Well, there's something accurate about it, but the way they show it, he's essentially saying there's a variability in the force. The force is turning on and turning off again. He literally said that, and by the way, that's not unusual at all. That's part of the whole paradigm. Now, the actual mechanism of that is what I described, but they haven't figured that out.
Remember, hydrogen bonds aren't really that strong. Compared to the oxygen and the hydrogen bond, covalent bond here, the hydrogen bond's pretty weak.
This is something they say over and over again when you look into the literature on H2O. They say the hydrogen bond is kind of weak. And then other instances where it does something like surface tension, they say, well, that's because the hydrogen bond is very strong. Now, they don't realize that what they're really saying is that the hydrogen bond is variable. Sometimes it's weak, sometimes it's strong. How can something be both strong and weak without there being some mechanism to cause that? And since they haven't discovered the mechanism, well, it's going to seem very confusing. But let's continue on.
Let's take a look at more water molecules, and I'm going to put the hydrogen bonds in right about room temperature. If you look at any one water molecule, you'll see that the hydrogen bonds are breaking and forming, but they do stay kind of attached together.
So they do stay kind of attached together, but yet they maintain this distance between each other. Is that really what's going on? What's really going on is that when H2O molecules are surrounding each other, they turn off each other's polarity, and therefore any energy that exists between them causes them to bounce. So, unlike this model, which shows them hovering, maintaining some distance between each other, what's actually happening is they're bouncing against each other. Every time they come together, they turn off each other's polarity, making it so they won't stick against each other. And that's the actual mechanism by which H2O is able to achieve this high viscosity, or I should say low viscosity, very fluid. Let's go ahead though.
Of water, it's cohesive, there's surface tension, it has a higher boiling point than similar liquids that don't have hydrogen bonding. The hydrogen bonding has a lot to do with how water behaves.
Now note that he talks about how the hydrogen bonding has a lot to do with all these other behaviors. But here's the thing. They assume this static force field that never changes. It actually collapses. Let's go ahead and demonstrate that now. So when an H2O molecule has 0 hydrogen bonds, it has full polarity. Now here we indicated the polarity by just indicating 100%. But as it continues to make hydrogen bonds with other H2O molecules, every time it does that, well, you have to adjust that polarity. So now it's at 75%. Here's another one. Now it's at 50%. Here's another one. Now it's at 25%. And here's the last one here. And of course, now the polarity of that molecule in the middle has dropped all the way down to 0%. It literally has it no longer has any polarity. And again, this is because H2O molecules are solvents of their own polarity, and they do that in 25% increments per bond, and they can form up to 4 other bonds with adjoining H2O molecules. If you think you have a constant force field and you're seeing all these behaviors, they're doing stuff that's inconsistent with constant force field, you're not going to understand why you're observing what you're observing. In the next video, we're going to discuss how this understanding of this inverse relationship between connectedness and strength of connectedness helps us understand the anomalies of H2O. To some degree, though, it kind of brings up a question of how did we ever get so confused about this, that it's taken this long to make the realization that was made in this video. And my answer to that is that the confusion has never really not been part of the paradigm. In other words, from the start, we just had a misconstrued understanding of H2O, and it seems to be innate. It seems to be something that has more to do with being human than it does with the subject being all that complicated. Now, one of the strange things you'll notice if you look into this field, and what you could do is actually look at some of the comments on YouTube videos where they present some of the explanations associated with the current paradigm, and you may be surprised, as I always am, to see that they're glowing reviews thanking the people who made these videos. And I just think it's incredible how they were presented with an explanation that was fundamentally flawed, and yet they're thankful. I don't really know how to explain that. I don't know how to explain that phenomenon because it kind of doesn't make sense. I can only look at it this way. When humans are presented with something that leaves them confused, and it could be anything. It could be the nature of, we can get into some deep philosophical topics about the nature of life itself, questions that don't seem to have any straightforward answers. We tend to get into this situation where we just want things to be kept simple. Out of that comes this kind of relationship between the public and academia. Academia will just give you a simple understanding that you can believe and doesn't require you to think. And the public's part of that equation is that they'll just pretend like they understand it. And then this continues over long periods of time, and you end up with this situation where you have this completely confused understanding, but nobody can see it. No one can admit to it. Nobody in academia will acknowledge it. Nobody can even recognize it, and everyone just kind of pretends. And I think that's what's happened here with our understanding of hydrogen bonding is there's just this culture of pretending like it makes sense, even though it really doesn't make sense. Well, now my understanding will help us make sense of it. In the next video, we're going to be getting a more explicit understanding of why the anomalies of H2O, these behaviors that previously had no explanation. There's going to be two basic types of phenomena. One of those phenomena has to do with that elasticity of the H2O bond and how that allows H2O to interact with energy in a manner that's very different from other molecules. And how underlying that is how structural properties emerge. And remember, those structural properties were simply due to the fact that under reduced situations of hydrogen bonding, the polarity goes up enough that you actually get some structural property. We're going to show how that interaction allows us to understand all of the different anomalies of H2O. Now, the most obvious one we're going to deal with is surface tension. That's structural, right? But there's another one too, and that's high heat capacity, and that's energetic. And we're going to show how understanding these two leads us to one that is really dramatic about what happens in the atmosphere when it comes to tornadic vortices. But anyways, that's what we're going to be doing in the next video. Again, my name is James McGinn. I'm president of Solvent Tornadoes. Well, until the next video.